Questions 8 through 10 on the 2017 Grade 12 Euclid Math Contest. In the diagram, line segments AC and DF are tangent to the circle at B and E, respectively. Also, AF intersects the circle at P and R and intersects BE at Q. As shown, angle CAF is 35, DFA is 30, and FPE is 25. Determine the measure of angle PEQ. In this question, we have to do what is known as angle chasing. So they've given us a few of them, and we've got to chase the rest. So first, let's just figure out what they gave me. CAF, so they gave me this guy is 35, that angle in there. And then they told me that DFA is 30, so DFA, this is 30 here. And FPE, this is 25. And they want me to figure out PEQ, so PEQ is this one in here. I'll just call that theta for now. Now the first thing I'm going to do is draw lines from what I believe is approximately the center of the circle to B and E, the tangent points. And that's important to do because those two are right angles, right? Because if you have a tangent, it makes a right angle with the line that goes to the center of the circle. So that's going to be our first thing to establish. Okay, so now let's start labeling. These two are radii. Since this is, I'll just call that O for the center. Remember, this is Q, so don't get confused. This is a radius, this is a radius. So that means this is an isosceles triangle. So if that angle is X, that angle is X. And then this triangle in here, well, that is a 30-90 triangle, and then therefore this angle has got to be 60. This angle right here. And then this angle would be 180 minus 60, which is 120. So see if I can squeeze that in there, 120. All right. And then this angle, just from there to there, I will call Y. And therefore, this angle in here, since all the angles of a triangle add up to 180, would be 145 minus Y. Okay, so before we proceed, let's talk about this. This is a right angle, and therefore this is also a right angle. And since this is a right angle, these two angles must add up to 90. So that means X plus Y is equal to 90. So that is our first established equation. Now, it's hard to see, but you've got these lines that intersect, right? So opposite angles would be the same. So this angle would be the same as this angle. So I have to blow that up a bit to let you see. This angle is the same as this angle. So in that triangle, that one right there, if I sort of drew it very briefly here, this was 120, this was X, and this angle is that 145 minus Y, like that. So from that triangle, we can deduce that 145 minus Y plus X plus 120 is equal to 180. And therefore, we get 85 is equal to Y minus X. So we got that, and those two equations we will now combine by adding them. And when you add them, you get 175 is equal to 2Y, and therefore Y is equal to 87.5. And therefore X would be equal to 2.5 if you substitute Y back into either one of these equations. Okay, do we have enough? Let's see here. Now I'm going to label this angle, I'll just call it Z, and that means this angle is also Z since it's an opposite angle. And then all these angles would be basically equal to 360. So 2Z plus 2 times the 145 minus y. And that would be equal to 360. Well, the y value we know is 87.5, so that's going to be 2 plus 57.5 is equal to 360. And therefore 2z, if we put everything on one side, it would be 360 minus 115. And therefore 2z is 245. So therefore z is 122.5. And now we get to the final step, which is looking at that triangle right there. And that triangle, 25 plus z plus theta is equal to 180. And therefore 25 plus 122.5 plus theta is 180. And therefore, if we solve for theta, it is 32.5. And that is what they wanted us to figure out, the angle PEQ. So angle PEQ is 32.5. In the diagram, ABCD and PNCD are squares of side length 2, and PNCD is perpendicular to ABCD. Point M is chosen on the same side of PNCD as AB, so that triangle PMN is parallel to ABCD, so that angle PMN is 90 degrees, and so that PM is equal to MN. Determine the volume of the convex solid ABCD PMN. The first thing I'm going to do is use this diagram, but draw some other lines onto it. So this is our diagram. Now, I hope you can see that the convex solid that we have to figure out the volume of can be calculated by first figuring out the volume of this entire shape. This entire shape that includes the dotted lines, that whole thing, and then subtracting from it these tetrahedra, this one and this one. If you do that, you will be able to get the volume. Now, one thing is for sure is that this is not a cube. So we have to take that into consideration first. So let's draw the cube to make it obvious as to why it's not a cube and what we have to subtract from the cube. If I draw these red lines, that makes it a cube. But I hope you can see that those red lines make it a cube, but without the red lines, it's not a cube. So what I'm going to do is draw a side view. I'm going to draw this side right here to illustrate what I mean. And that side, because it's a cube, will just be a square. And what we have done essentially is we've chopped off a segment like this. And when you chop off that, that is what's left. And from that, we have to subtract the tetrahedra. Now, what's really important in this question is to first figure out this distance from here to here. It's 3D, so it's kind of hard to see. So what I'm going to do is I'm going to draw that PMN triangle down here. And that PMN triangle is basically like this. This is PMN. It's a right angle, so like this. And what I need to do is figure out the distance from there to there. That shouldn't be too much of a problem. This is P, this is N, this is M. We are told this is a right angle, and we are also told that this equals that. And then PN was part of a square of side length 2. So this is 1, this is 1. This is a right angle. So that means that this is 45 degrees, this is 45 degrees, so this is isosceles, and therefore this is also equal to 1. So that is equal to 1 right up here. So that means this distance from there to there is 1. And therefore, when I take the cross section like that, this side will be 1, and this is the part that I have to subtract from the cube. So let's do that. The cube is basically a 2 by 2 by 2. And then from that, I have to subtract this cross section. So that is going to be 1/2 the area of this triangle. It's a 1/2, so 1/2 base times height, so 1 times 2. And then, of course, I have to multiply by the fact that this is a cube. It extends, right? It's a cube. And when it does extend, that side over there is 2. So the volume of that chunk that is cut out would be 1/2 base times height times 2. Because remember, we're calculating volumes. All right, so now what we've done is we've figured out the area of this diagram without these red lines. With the red lines, it was a full cube. Without the red lines, it will be this right here. So let's subtract the red lines since we've already figured out the area. So this right here represents the area of this entire shape with the dotted lines. But we don't want the dotted lines. We want just A, B, C, D, P, M, N. So how do we subtract these tetrahedra? Well, there's 2 of them, and they're identical since this diagram is symmetrical. So it would be 2 times the area of the tetrahedra. Okay, the area of each tetrahedra, that is, if you remember the area formula, 1/3 times the area of the base times the height. Like that. So 1/3 area of the base. Well, the base of each tetrahedra is right there. And the height is top to bottom, like that. So the top to bottom, that's pretty straightforward. Top to bottom actually would be represented better by that line right there. And that's just 2. So the height is the easy one. The area of the base, well, it won't be that difficult. We just have to do a little bit of calculation there. The area of the base, I can go back to this diagram right here. No need to create another diagram, just this one right here. So if I were to extend those lines and then to draw a line straight across, that would give me the base, where this is R. And this is the base right here. And those dimensions are 1 and 1. And that's it. So from here to here is 1, and from here to here is 1. So that's just a triangle, 1/2 base times height, 1/2 1 times 1. So this gives me just 1/3. So that's it. Now I can use this formula to figure out the volume. So the volume is going to be 2 times 2 times 2 is 8. And then 1/2 times 1 times 2 times 2, that is just 2. And then minus 2 times 1/3, because each tetrahedra has a volume of 1/3. So this looks like 6 minus 2/3. So that's going to be 18 minus 2 over 3. And that is 16 over 3. 16 over 3 is the volume of that convex solid A, B, C, D, P, M, N. A permutation of a list of numbers in an ordered arrangement of the numbers is an ordered arrangement of the numbers in that list. For example, 3, 2, 4, 1, 6, 5 is a permutation of 1, 2, 3, 4, 5, 6. We can write this permutation as A1 through A6, where A1 is 3, A2 is 2, and so on. Determine the average value of the absolute value of A1 minus A2 plus A3 minus A4 over all permutations of 1, 2, 3, 4. Well, 1, 2, 3, 4, there's only 4 numbers, so we can pretty much make this list, because the number of permutations, 4 choices, 3 choices, 2 choices, and 1 choices for A1 through A4, and that is 24. So there's only 24 permutations. So since we're trying to understand this question, let's just do it the manual way, the long way. So we'll make a table and we'll fill it out. We are going to put A1 here, A2 here, A3, and A4. And then over here, of course, we're going to calculate the absolute value of A1 minus A2 plus the absolute value of A3 minus A4. So, for example, 1, 1, 1, 1, 1, 1, and then we can easily just figure out the other permutations. And since there's so few of them, we can just complete the list manually and figure out the total and then the average. So 2, 4, and then what I'll do is I'll just do the first few, and then of course I'll just fill out the rest. I don't think you need me to talk you through every single one. I'll just do the first few. Okay, so for the first one, A1 minus A2, absolute value is going to be 1, and then A3 minus A4, absolute value is 1, so that is equal to 2. Second one, same story. 2 minus 1 is 1, 3 minus 4, 1, and then of course 2. And then so on, right? So 3 minus 1, that's 2. 4 minus 2, that's 2, so this is 4. So in a very similar way, I'll fill out all the other ones. So there you go, I filled it all out, and it was pretty much the same as the first few that I had done. Now we have to figure out the average. So we have to add up all these guys and divide by 24. So let's see, I've got, how many of these 2's do I have? I think I have 8 of them, right? These 2's, 1, 2, 3, 4, 5, 6, 7, 8. And then the rest are 4's. So 24 minus 8, 16 of those 4's. And I've got to divide by 24. So that's 16 plus 64 over 24. And that is 80 over 24. Divide top and bottom by 8. And I get 10 over 3. So there we go. That is what they're asking for. Part B. Determine the value of A1 minus A2 plus A3 minus A4 plus A5 minus A6 plus A7 over all permutations of 1, 2, 3, 4, 5, 6, 7. Well, Part A usually leads into Part B. So that's why Part A is important to understand fully. And just one quick thing I want to point out about Point A before I tackle Point B. Notice something which I think is interesting. When you add up all of these guys, you will get 60. If you add up all of these numbers, you will get 60. Similarly, 60 and 60. And that's not just a coincidence. That's because the same numbers were used in each of those 4 columns. They just were rearranged. So that's very important because that is something we're going to use in the next question, Part B. So here we go. Now there's 7 numbers, right? So just as before, how many permutations are there? 7 times 6 times 5 times 4 times 3 times 2 times 1, and that is 5040. So obviously we're not going to do it the manual way. That would take absolutely forever. So we have to do it some sort of shortcut. Well, when we were in the process of, let's say, writing out these different permutations, the first one would be some A1 minus A2 plus A3 and so on. Whatever numbers we chose. And then similarly, the second one would be a different sort of scenario, different numbers. And then what we would have to do at the very end is add them all. So eventually you're going to get dot, 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 and you're going to get 5,040 of these, and you're going to add them all up. And then, of course, you're going to divide by 5040. So what I'm going to do is just call each of these a certain S. So this will be S1, just all the A's. And remember, all the A's are going to be different. Just because they're called A doesn't mean they're the same. So that's very important to remember. All of these, whatever they are, dot, 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 I'll call S2. And then similarly S3, S4, S5 to denote the sums of each of those columns. And remember, this is minus, this is plus, minus, plus, minus, plus. Okay. So since all numbers will appear in equal amounts in each column, all the sums will be equal. And that is directly illustrated by this example right here. You notice how the sums at the bottom were all 60. Same story here. And I just wrote it out in sort of a sentence format that since all the numbers will appear in equal amounts in each column, all the sums will be equal. So that means all of these guys are equal, just how previously they were all 60. These will all be equal. The number, however, I don't know yet, but I do know that S1 will be equal to S2, will be equal to S3, and so on. S5, S6, S7. So that helps tremendously, I think, because now we can take this guy and just put S1 for everything. So S1 minus S1 plus S1 minus S1 plus S1 minus S1 plus S1. And this just reduces to just S1. This cancels, and that cancels. All right, that's great. So that means the average, since the entire sum is just S1, the average would be the average is the sum divided by the total number of permutations, which we had previously calculated as 5040. But obviously, I have to figure out what is S1, the numerical value for S1. And again, I'd like to go back to that example. Why not? If it explains it in simple terms, why not use it? I figured out 60 by adding up all of these, right? So what's a simple way of doing that? Well, it was basically 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4. Correct? So that was 6 plus 12 plus 18 plus 24. And that is, of course, equal to 60. Now, how did I get these numbers? Well, obviously, I just got them from the table. But is there a simpler way? I think so. How many numbers were there in total? Well, we had calculated that there's 24 permutations. Okay? So you take the 24. And then, how many different numbers were there? It was 4. So you divide that by 4, and that gives you 6. That's why each of these numbers had to be multiplied by 6. So the same story here. This time we went from 1, 2, 3, 4, 5, 6, 7, right? How many permutations were there? Well, we got 5040. How many numbers are there? Well, there's 7. So 5040 divided by 7 is 720. And that's the number. We have to multiply each of them 1. So S1 would be 720 times 1 plus 720 times 2 plus 720 times 3 plus 720 times 4, and so on. 720 times 5, 720 times 6, plus 720 times 7. And when you do that math, you get 720 times 28. And I think that is good enough for now. I can just put that in there. So 720 times 28 over 540. And when I do that math, I get finally the answer, which is just 4, interestingly. So there you go. 9B. Determine the average value of A1 minus A2 absolute value plus A3 minus A4 absolute value plus ... all the way to A199 minus A200 absolute value over all permutations of 1 to 200. Well, as before, in the very first example, if you remember, there was 4 factorial permutations, which was 24. In the second, part B, there was 7 factorial permutations, which was 5040. This time we got 200 factorial permutations, and I'll just leave it as 200 factorial. And then we've got this big, long expression. And just as before, instead of worrying about what they will be, I'll just call each of them a certain S. S1, S2, S3, like that. Plus ... all the way up until S99, and then there would be an S100 in there. all of those permutations when you add them all up. And as before, because of the symmetry and the fact that all the numbers are equal in each column, S1 equals S2 equals dot 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 S99 equals S100. So this whole sum really is just 100 times S1. And therefore, in the very end, when you do the average, it would be 100 times S1 divided by the number of permutations, which is 200 factorial. Okay, so now we have to figure out the numerical value of S1. So here we go. Before we calculate the numerical value of S1, we have to understand that when you first have this term A1 minus A2, we can choose something to be A1 and choose something to be A2, and that's fine. But then there's going to be, of the 200 numbers, 198 numbers left over. And those 198 choices are available for A3. And then there would be 197 choices available for A4, and so on. So each of these gives, combined with all of these guys, 198 factorial permutations, right? 198 times 197 for A4, 196 for A5, and so on. But then the story doesn't end there, because when you have A1 minus A2, we're giving actually a absolute value, and that's similar to A2 minus A1. So we have to actually multiply this by 2. There'll be 2 times that many. So it would be 2 times 198 factorial. That is what we will have to multiply the sum that we get for this guy, all the different possible sums. So here we go. Let's do that. Let's keep this. So we are concentrating on A1 and A2. And in particular, we want to figure out A1 minus A2 absolute value. So we'll call this initial sum D, and then at the end we'd have to multiply by the number of different permutations. This is a long story here because it could be anything. You could have 2 and 1, for example. That would give you 2 minus 1. And remember, it's absolute value, so always going to have positive. Or you can have 3 minus 1. And in the first sort of row, I'm just writing out when you subtract 1. So as you can see, it's 2 minus 1, 3 minus 1, and then dot, dot, dot. It'll be all the way till 200 minus 1. And then you have combinations where you subtract 2. So it'll be 3 minus 2 plus 4 minus 2 plus 5 minus 2, right? All the way dot, dot, dot until you get the very last one, which would be 200 minus 2. Then subtract 3, right? So 4 minus 3 plus 5 minus 3. And then as you can see, this keeps on going until you get to 200 minus 3. And so on, right? You get the idea. So eventually you'll get to subtracting 198. So that would be 199 minus 198 plus all the way till the end, which would be 200 minus 198. And then the very last one is 199, so that would be just 200 minus 199. So this actually would cover all of the bases, would cover all of the different possible scenarios. Now what we can do is we have to add all these up. And you can add it up in any way you'd like. I'll just show you one way that has some kind of fancy mathematics. We're going to add it by column. So that column, then this column, and so on. When you add by column, as you can clearly see, it would be as follows. The first column would be, it's all going to be ones, so it's 199 times 1. Second column, these guys are all 2's, so it's 198 of those times 2, because this one doesn't have one. This one does. And similarly, the pattern sort of is very predictable. The next one would be 197 times 3, and then dot, 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 all the way until you get to the very end, which would be 2 times 198, and then finally 1 times 199. So now, this is something you have to add. So this is where I will write fancy mathematics. Okay, so let's see. Hopefully I can explain this without confusing anybody. The first one is 199 times 1, right? But instead of writing 1, I'll write 200 minus 199. It'll become apparent why later on. The next one is 198 times 2, but instead of writing 2, I'll write 200 minus 198. And similarly, the next one is 197 times 3, but instead of 3, I'll write 200 minus 197. And then this keeps on going, dot, dot, dot. And the very last one is 2 times 198, but instead of 198, I'll write 200 times minus 2. And the last one, instead of writing 199, I'll write 200 minus 1. Okay, so now let's see what happens. We can notice that there's a 200 everywhere. So when you multiply it out, you get 199. And then from here, you get a 198. And then from here, you get a 197. And this just keeps on going all the way down to 2 and then 1. So 2 plus 1. And then when you do the next multiplication, you'll notice that you have to subtract, but it'll be 199 squared. That times that, 198 squared. This times this, 197 squared. And so on, all the way down to 2 squared, and then 1 squared. Now this is much more easier. This you can solve with that formula. I'm sure that one everybody knows. N times n plus 1 over 2, the sum of consecutive numbers. So that's just going to be 199 times 200 over 2. The next one, however, not as many people know. That is adding consecutive perfect squares. Some of you know that one, some of you don't. No problem, I'll mention it. It is n times n plus 1 times 2n plus 1, but all over 6. So that's going to be 199 times 200. I'm adding these guys. Times 199 times 2 plus 1, all over 6. So as you can see, this is much more workable. So let's do this math now. So it looks like 100 times 199 times 200. And this is 1/6 times 199 times 200, and that's 399. Okay. Let's see here. There's a 199 and 200 that we can factor from both of those. That's just going to leave 100 times 399 over 6. And that is 199 times 200. When you do that fraction, it becomes 201 over 6. And in lowest terms, it's 199 times 200 times 67 over 2. So that is my D. And as previously stated, don't forget that you have to multiply it by that because that's how many permutations you have. So that means S1 is this 199 times 200 times 67 over 2 multiplied by that 2 times 198 factorial. Okay, well, let's see here. 198 factorial times 199 times 200 becomes just 200 factorial. And then times 67, these 2's cancel. So finally, the average is S, if you remember, 100 S1 over 200 factorial. And that was from all the way here. We had established that 100s1 over 200 factorial. So that is going to be 100 times 200 factorial times 67 all over 200 factorial. And the 200 factorials cancel and you get just 6,700. And that's the answer. Consider a set S that contains m greater than or equal to 4 elements, each of which is a positive integer and no two of which are equal. We call S boring if it contains 4 distinct integers, a, b, c, d, such that a plus b is equal to c plus d. We call S exciting if it is not boring. For example, 2, 4, 6, 8, 10 is boring since 4 plus 8 is equal to 2 plus 10. But 1, 5, 10, 25, 50 is exciting. Find an exciting subset of 1 through 8 that contains exactly 5 elements. Well, got some experimentation here. We've got 1, 2, 3, all the way up until 8. And we've got to choose 5. All right, well, let's try just 4 and see what happens. This one will not be exciting. It'll be boring because 1 plus 4 is equal to 2 plus 3. So very quickly, the first 4 don't work. So I think I might have to take out that 4 and then put in a 5. Let's see if that works. Let's first figure out the sums. 1 plus 5 is 6. Actually, let me just do it in order. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 5 is 6. 2 plus 3 is 5. 2 plus 5 is 7. And 3 plus 5 is 8. Are any of these the same? 3, 4, 5, 6, 7. No. So that means this is exciting. Great. So I will keep these 4. And let's see if I can add a 5th number to make the set of 5 numbers exciting. Okay, so now the search is on for that 5th number. If that number is a 6, does this work? I don't think so, because 2 plus 6 is equal to 3 plus 5, right? Both of those are 8. So that can't be a 6. Okay, no problem. Let's keep going. Let's see if it's a 7. Does that work? Do I get an exciting subset? And let's see here. 3 plus 5 is equal to 1 plus 7. So I don't. So the rule is that I should not be able to get 2 equal sums. All right, let's try 8. And 8, I will check in a thorough way. Let's get all the sums. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 5, 6. 1 plus 8, 9. Then 2 plus 3, 5. 2 plus 5, 7. 2 plus 8, 10. 3 plus 5 is 8. 3 plus 8 is 11. 5 plus 8 is 13. So as you can clearly see, none of these are the same. So therefore, that means this is exciting. Great. Prove that if S is an exciting set of m greater than or equal to 4 positive integers, then S contains an integer greater than or equal to m squared minus m divided by 4. All right, so S, they're saying, is a set with m elements. So from m, choose 2, and that represents the number of pairs. So this represents the number of pairs. So for example, in this case, I had 5 elements. M was 5 in this case. And from 5, I can choose 2. And 5 choose 2 was 10. And that's how I got 10 pairs. As you can see, those are 10 pairs. So m choose 2, that's going to be m factorial over m minus 2 factorial over 2 factorial. And that is just m times m minus 1 over 2. So this number, m times m minus 1 over 2, represents the number of pairs. Now, S is exciting, right? So that means the sum of the pairs are all different. Just like how over here, the sum of all the pairs was different. That's the criteria for becoming exciting. Same thing here. The sum of all the pairs has to be different. Now, there are this many pairs. And therefore, there are that many different sums. So over here, there was 10 different sums. If we have m, it would be m times m minus 1 over 2 different sums. And for example, the sums, not necessarily, but in this case, the lowest sum can be only 3, right? Because 1 plus 2 are the smallest possible numbers. So 3, 4, and then it goes all the way up until there's m times m minus 1 over 2 different sums. So for example, in this scenario, there was 10 different sums, and since the smallest sum is 3, and each sum has to be different, the other sums could be 4, 5, 6, all the way up to 12. And therefore, that largest sum has to be either 12 or greater. And in this scenario up here, my m times m minus 1 over 2 was 10, this guy. So the largest sum has to be greater than that. So the largest sum must be greater than m times m minus 1 over 2. So for example, in the pairs up there, the largest sum was 13, and that was indeed greater than the number of pairs, which was 10. So that is an important fact. Now we have to consider the fact that we have a pair that consists of two numbers, say a plus b. And we have established that this sum is always going to be greater than m minus 1 over 2, where a plus b represents the largest sum. Then one of these numbers, say a, has to be greater than half of this, m times m minus 1 over 2. For example, if the numbers were, say, 5 plus 8, and that is greater than 10, just like we had up here, right? 5 plus 8 was 13, and that's got to be greater than 10, which represented m times m minus 1 over 2. Then that means that if we add this, it would be 13 over 10. And even if those numbers were equal, they would have to be at least 5 and 5. At least. But they can't be 5 and 5 because the numbers have to be different. So you would have to have at least something like 4 plus 6 for it to be, say, equal to 10. So if A is the larger of these two, say A was greater than B, then A has to be greater than half of this number. In this case, half of 10, which is 5. And as you can see, 6 is definitely greater than 5. So the same sort of philosophy there. So that means A has to be greater than m times m minus 1 over 4. And that shows that at least one number in that set is greater than or equal to m times m minus 1 over 4, which is the same as m squared minus m over 4. And that is what they wanted us to figure out. Prove that if S is an exciting set of m greater than or equal to 4 positive integers, then S contains an integer greater than or equal to m squared minus m over 4.